All right, so we're going to try things a little bit different. For you guys, you're a little lucky. In some other classes, I don't have a station and a setup where I can get anything where there's a whiteboard behind me. I'm going to try to use this. I brought the one I was using for the other ones today. But even in class, if I'm not writing big enough or you can't quite see this, when I'm writing, it'll be up here as well. So we'll give that a try today. I know that kind of sorry for the craziness of last week and kind of being out and wanting to try to do it Monday and then canceling. But like I said, we're actually kind of pretty close to being caught back up. I'll likely do an additional video and post it this weekend. It'll be pretty short, kind of like the last one, maybe 20 minutes, just to kind of make sure we get caught up to where we should be. I'm also, this is a little bit off the top of my head, but I might put out another poll because I haven't been getting as many emails or notices about people that can't be coming to class, and we still don't have a lot. So if you do want to be attending like every class, I want that to be an opportunity if other people aren't going to show up. So I'm probably going to put out another poll. Try to be really honest with whether or not you're going to kind of show up and want to show up to class. That way maybe we can get everybody in here more often during the week. Okay? So let's go to where we left off, I think. Actually, let me make sure. Yeah, okay, we're good. So I put up another kind of, jeez. Sorry if that was as loud for people on Zoom as it was for everyone here. I might have to edit that. Okay, so I put up another thing of lectures. Some of it's kind of what was in the end of the week 3 lectures, but I just want to kind of give us a nice starting point for being in class today. So one thing I think we left off, we didn't really talk about last class, is this idea of conditional probabilities. All right, so we can rewrite, if we usually don't have this conditional probability, but we can rewrite it as the probability of the intersection of these two events, right? And then divide by the probability of whatever I'm conditioning on. So here, this vertical line, remember, I briefly introduced it, means given that A has occurred, or conditioning on A, right, what's the probability of B? So what we would call this is the conditional probability of B, right? We're still interested in the probability of B, it's just now we've conditioned on that A has already occurred, right, or given that A has occurred. So to find that conditional probability, take the intersection of the two, and then divide by whatever we conditioned on. Right? Notice here, if I wanted to find the conditional probability of A, the probability of A, but conditioned on B, I would take the intersection of those two, but now I'm conditioning on B, so I divide by the probability of B. Okay? So why is this true, right? Why does this have to hold? I'm getting my markers here. I'll grab those. That was downstairs. So why does this have to be the case, right? We can think about, let me blow this up here. Minimize myself, right? Okay, so you can see this, all right. So if I have this experimental outcome space, right? Now let's think about it's the easiest way to do this. Let's go, let's say this is my event A, right? This little kind of like rectangle down here. Let's say the probability of A is 0.25. I try to draw it to scale, but maybe it's not perfect, right? So if I then have this block here, and I say this is event B, right? And let's say the probability of B is something like 1.25. Okay? So I have the unconditional probabilities, right? But what if, and I'll just write it in here, what if I wanted the probability of B given that A has already occurred, right? Well, I know that the conditional probability is simply the intersection of the two, and then divide by the probability of whatever I'm conditioning on. Right? So if I look at this, the intersection of the two, and here I guess you can kind of see like B is 1/2 of A. So the intersection here isn't like directly given to us, but you can kind of imagine just the visual space. So we don't need the numbers necessarily, but the visual. Where does A intersect B here? Well, it's just this guy right here. And once I've conditioned on A, what I'm really saying is I'm not looking at the entire experimental outcome space anymore, right? Before I was looking at this space of 1. Once I condition on A, I'm saying I know now that I'm somewhere in this little area. So I've reduced my entire experimental outcome space from 1 down to 0.25, right? And of that area of 0.25, 0.125 of it is where A and B kind of overlap. Even if B wasn't completely all in here, so let's say here's A, but that B like went out this way. Well, once I condition on A, now I'm only looking at this part of B that overlaps with A. And so that's kind of where the intuition comes from behind why that multiplication rule works, right? Once I've conditioned on something, I'm no longer looking at the entire experimental outcome space of 1. I'm limiting it down to whatever the area is of that thing I've conditioned on. Okay? Any questions on that, or couldn't quite see something? If you have a question, feel free to ask. Let me check the chat here real quick. Okay. Let's get this over here. All right. So that's kind of the intuition behind why this holds, right? We talked about these rules last class. This is just kind of putting them all on the same slide. Notice we can rearrange that rule to look like this. It doesn't matter. Mostly, I think even what we're going to do today, we're primarily going to be using kind of this form of that multiplication rule, and not this, rearranging things. We won't really need it in this format. So using this idea of conditional probabilities, the next thing we want to talk about is whether or not events are independent, right? And how do we check for independence, okay? So the idea of the two events being independent is that if the probability of A, once I've conditioned on B, is the same as just the probability of A not conditioned on anything. So if the conditional probability of A is equal to the unconditional probability of A, right, we would say those are independent events. So the example I always give instead of numbers here, let's think about eye colors, all right? Well, probability if I choose someone at random to have blue eyes, right? I don't know, 0.2%, let's say, or not 0.2%, 20%, so 0.2, probability of 0.2. If I then told you, okay, what's the probability if I chose someone at random, they have blue eyes, conditioned on or given that that person is a male? Well, as far as I know, there's no differences across male, females in the likelihood they have blue eyes, right? And so that additional piece of information, that it's a completely independent event from eye color, right? Gender and eye color, at least, like I said, I'm not a biology expert, but that's what I believe is true. If someone checks me on that, then yeah, I could be wrong, but I'm pretty sure that's true, right? And so if I look at kind of that conditional probability, it'd be the same as the underlying probability that someone had blue eyes with no additional information, okay? So it would have to be something that these two things are completely independent, okay? Vice versa, we could also say if the conditional probability of B is equal to the unconditional probability of B, then A and B are independent as well. We can check either one. And it's kind of like we said before, if A and B is the same as B and A, if A and B are independent, B and A are independent, right? It doesn't matter which way I say it both will be true. So I can check this either way, and I only have to check them. I only have to check it one way to prove that these events are independent, okay? So if I go back and I look at that multiplication rule, so I said we won't be using this one very much. We're going to alter a little bit, and then we're going to use it. So here's the multiplication rule that we have, right? It can be in either form. Just here, it was just a little bit of algebra to go from here to here. So if I use that, I know if they're independent, that this has to be true, that the conditional probability of B is the same as the unconditional probability of B. So what I can do is I can just substitute in here the unconditional, just the probability of B. Once I have that, I have this other check for independence. While this isn't like the definition, right? The definition is kind of up here, that the conditional and the unconditional probability are the same. I know that if they are independent, this has to hold. that the probability of the intersection is just equal to the probability of A times the probability of B. And why this helps us out is you can think about, if I had a contingency table, these are a lot easier to find. The contingency tables don't give me any conditional probabilities, and so I'm going to have to be working with intersections in the probability of the events themselves. So this is kind of one nice way we can check for independence, and I'll show you an example in here in just a second using that contingency table. Okay? So talking about events being independent, I kind of try to give you that eye color example. We can also think about there's a lot of times where we have dependent events, right? And we'll start an Excel example today. I don't think we'll get through it, but Friday I'll kind of revisit and we'll see whether or not they're independent in the Excel example that we're doing. But dependent outcomes would be something like this. Let's say event A is whether or not someone votes in a national kind of, I don't know, we have some national thing that we're voting on, but whether or not we want to legalize marijuana nationally, right? And let's say that underlying probability is 0.5, right? If I chose one person at random, the probability they vote yes to support that would be 0.5. Well, if I'm still interested in the probability that someone votes yes to support nationally legalizing marijuana, but then I say, conditioned on, you know that that person that you're asking is Republican, right? What do you think would happen to that probability? It's probably not 0.5 anymore. It's probably lower, right? If I condition on that person being Democrat, that conditional probability is probably higher than the unconditional probability. So more often than not, we do have dependent events, right? Having that additional piece of information does influence the probability. But occasionally we can have these independent events, and this is how we check for it, right? So here's our definition of independence, right? We've got the conditional probability of A. If it's equal to the unconditional probability of A, they're independent events. Well, we can get the probability of A pretty easily from this table, right? What's the probability of A here? The way I read this contingency table, I just go to the total column, right? So the probability of A is 0.6. So if the conditional probability of A, right, A conditioned on B, if that's also 0.6, we have independent events. But I can't directly get this conditional probability from my table. But what can I do? Well, I know I can rewrite the conditional probability as the probability of the intersection of those two events, and then divide it by whatever the probability is of what I'm conditioning on. So I'm conditioning on B, so divided by the probability of B. Now these two things, right, which I know is equal to the conditional probability, are pretty easy to find from my table. What's the probability of A and B? Well, remember, those top four left cells represent intersections. So the probability of A and B, or A intersection B, which is what this downward facing or the upside down U is, the probability of A and B is 0.15. So I go ahead, plug that in, divided by the probability of B, which is 0.25. 0.15 over 0.25 is 0.6, which is what we originally said, well, that's just the unconditional probability of A as well. So these two things are the same. So we have independent events. Okay? Does that make sense? Any questions on that before we keep on moving? Okay with this? Okay. So we could also check it the other way, right? If the conditional probability of B is equal to the unconditional probability of B, we would also have independent events. Now, it's going to lead us to the same conclusion. I'm just going through this for the sake of going through it. We don't have to check it both ways. But we could have instead started here, right? So what's the probability of B? Probability of B is 0.25. So if the conditional probability of B, once we're conditioning on A, is equal to 0.25, we've got independent events. We can rewrite this conditional probability as the intersection of the two. And here, if you're confused a little bit, even if I would have written this as B intersected with A, it doesn't change anything, right? Because A and B is the same as saying B and A. But if it makes a little bit more sense to you, and you want to like edit these slides to make more sense to you, you could have written it in. I could have had it like this as well, right? Because the intersection of B and A is still 0.15. Divided by the probability of what I'm conditioning on, the probability of A, which is 0.6. 0.15 over 0.6 is 0.25, which sure enough, that was the unconditional probability of B as well. So no matter which way I checked it, both ways would have shown me that these two events are independent. Okay? Any questions on that before we keep moving? So there's one more check, and then I'm going to kind of draw something for you and revisit this. But remember, we said if they're independent events, that this would also have to hold. That the intersection would just be the product of each of those probabilities, or probabilities multiplied by each other, right? So I can find the intersection of these two events pretty easily. Probability of A and B is 0.15. The probability of A is 0.6. The probability of B is 0.25. So if 0.6 times 0.25 is equal to 0.15, they'd be independent events. Sure enough, if you plug this into your calculator, it is 0.15. It's another way we could check for independence. I think this way is probably the easiest, right? Because it's very easy to grab that intersection from the table, and it's very easy to grab the probability of A and B. And so if this holds, if these two things are equal, they're independent events. If they're not equal, we would say that they are dependent events, right? Or not independent, I guess is another way you could say it too. Okay? Any question? And this came from, remember, if I can stop scrolling so fast. This came from this idea, right? If we had that multiplication rule and we knew they were independent, we could just plug in the unconditional probability here. Right? That's where I was kind of grabbing that from. We had talked about it a few previous slides back. Okay. Another thing I wanted to mention here is, and this is just kind of a byproduct of, we're not going to go through like the formal proof, but I'll give you some intuition behind why here in a second. If we have two events that are independent, their complements will be independent as well. So I could check to see if their complements are independent by simply looking at A complement, B complement, A complement, B complement, right? And see if the intersection of the complements is equal to just the probability of each complement multiplied by each other. That's going to show me that the complements are independent. Well, sure enough, the probability of A complement and B complement is 0.3. The probability of A complement, 0.4 times the probability of B complement, 0.75. 0.4 times 0.75 ends up being 0.3 as well. So if I have two independent events, I know their complements will be independent events as well. Okay? And here I'll try to give you a little bit of intuition behind why. So go back to my example where I said, you know, the probability that somebody has blue eyes is the same as the probability they have blue eyes given that they're a male, right? It doesn't change the underlying probability at all. Well, those are events A and B, right? Having blue eyes and being male, right? So if those are independent, the complement should be independent as well. So the complements would be the probability that somebody has non-blue eyes is equal to the probability that somebody has non-blue eyes given that they're female. Well, yeah, knowing that they're female doesn't change anything about their eyes. So just, you know, anytime we have independent events, we know the complements will be independent as well. Right? And I wanted to give a little bit better visual maybe behind what independent events would look like. And this is like a kind of I don't want to say I'm cheating with this example, but it maybe oversimplifies it, but I do like it. So let's say I have this experimental outcome space. Let's get rid of me so there's not two of me. Let's say I have this up here is event A, right? And the whole box is my entire experimental outcome space. Right? So you can kind of see, like, I try to draw it to scale, but the probability of A is 0.5. Right? Then let's say I've got event B, which is over here. Okay? And it also, you know, if it was drawn perfectly to scale, cuts that experimental outcome space in half, just the other direction. Right? So we've got event B here. Okay? So if I said, what's the probability of A? It's 0.5. What's the probability of A conditioned on B? Well, if I condition on B, I know that I'm only now dealing with this part of the experimental outcome space, right? Just what's in B. I now know that my area of possible outcomes left has fallen from 1 to 0.5. And of that space of 0.5, how much of it is also in A? Well, you can kind of imagine, if I drew this to scale, what should this area be? If it exactly split it in half both ways, this area would be 0.25, right? Because I should have 4 equally sized kind of squares there. And what this area actually is where event B and event A overlap, or that's the intersection of A and B, right? And so if this area is 0.25, out of the entire space that I conditioned on B of 0.5, 0.25 over 0.5 is 0.5. So that conditional probability of A hasn't changed at all. And it's because what has to be true about independent events is kind of, you can think about like the proportion of the entire population that is this event you're interested in would have to look like the same proportion of whatever you've conditioned on, right? It's the same proportion of the space of whatever you conditioned on as it is for the general population, right? The probability that everyone in the population has blue eyes is the same as the probability of people that have blue eyes that are male, or probably the people with blue eyes that are female. And this is kind of like the reason why, right? Because half and half either way. So kind of you know, sometimes that clicks, sometimes it doesn't, sometimes it helps people kind of think about it better. I you know, try to be comprehensive in showing you the things several different ways and try to talking through them several different ways. So that's kind of the idea behind independence, okay? Let's see, what did I have next? So let's say we had a sample question that looks something like this, right? If I gave you a contingency table, we're stepping away from independence a little bit now, just using that multiplication rule. And let's say I just wanted to find a conditional probability, okay? So what's the probability of R1 given C2, right? So R1 given C2. So if I want to find R1 given C2, the first thing I need to do is rewrite my conditional probability, because I can't find directly a conditional probability on this table, right? So I might do something like this. This is how I would do it. I want the probability of R1 given C2, right? And you could write it next to it. I think sometimes it helps with this one to write it like directly underneath, because you know that the conditional probability will just be the intersection of these two events, R1 and C2, divided by whatever you're conditioning on. Here we're conditioning on C2, right? So now we'll find the intersection of these two things, divided by the probability of what we conditioned on, and then that will give us our conditional probability that we were originally interested in. So go back here. You can almost even see that in the background. I can actually make this bigger. So we want the intersection of R1 and C2. So R1 and C2 is 0.2, divided by the probability of what we condition on, which is C2. The probability of C2 is 0.5. So kind of write that out here. You can find the intersection is 0.2. The probability of C2 is 0.5. Gives us that conditional probability we wanted, which is now 0.4 once we do the math. Okay. Any questions on how on that one, or if something changed, what would I do, or we're okay with this? Yes? Okay. All right. I think I'll have this discussion now, and then we'll kind of do a little bit of Excel work to end. Well, I didn't get super far with the other class, so I'll go through this. We'll talk about this, and then we'll do a little bit of work Excel to end the class. We'll have a shorter class, I think. So we know that the probability that a coin flip comes up heads is 0.5. Right? If I flip a fair coin, the probability it comes up heads is 0.5, right? Over the long run, if I could flip a coin an infinite number of times, I know that 50% of those flips would be heads, 50% would be tails. You know, if I flip a coin 10 times, I might end up with 9 out of the 10 being heads, right? But over an infinite space, I know that it would be a 50-50 breakdown, okay? Coin flips are independent. So if I flip a coin over and over again, each coin flip is an independent event, right? So if we have independent events, right, then the probability of this coin flip is completely unchanged by if you tell me the previous coin flip came up heads, right? It's like telling me that someone's male or female doesn't change the probability they have blue eyes, okay? So what ends up happening is a lot of people, if they see like a string of flips come up heads, they automatically think, well, it's come up heads 4 or 5 times in a row. This has to balance out at some point, so the probability it comes up tails this time has to be higher. No, they're independent events. The underlying probability is always 0.5, and so they start to fall victim to what we call the gambler's fallacy, which is that things have to like kind of weigh out. And I put Kenny Rogers here because of the gambler. If you don't know who he is or that song, then I pity your soul. But no, I'm kidding. But you should look it up. It's good. So, you know, we could think about if I see a long run of tails, is it more likely I see heads in the future? No. In fact, I simulated that, you know, how you could do this in Excel with some random number generators, and you can get either a 1 or a 0. And then you can look and see every single time after there was a tails, or like, I think I coded tails was probably a 1 and head was a 0. But every time there was just one tail in a row, the probability that it was head on the next one was actually about 0.5. After you saw 2 tails, the probability it comes up heads the next time is about 0.5. I mean, it's a little off here, but not much. 3 in a row, probably 0.5. 4 in a row, probably its heads is still 0.5, right? It isn't changing at all, okay? So we can kind of prove this to ourselves with some data, but in practice, we see a lot of people falling victim to this. So I got a chintzy example here, but we see it in a lot of other areas that maybe matter a lot more, which is something like if I see, you know, it's almost, it isn't quite, well, you think about it this way. I know some people will see like, oh, well, you know, I know the stock market returns on average about 10% every year. So if the last 4 years it's returned above 10%, I know this year it's got to return less, right? Well, not necessarily. Like today is completely independent, you know, from 5 years ago potentially. Not completely, but for the most part, it could, you know, depending on what you're investing in. And so if we look at actual gambling habits, we see it all the time, right? So there's this example in 1913. You have this roulette table, and, you know, for the sake of the discussion, there is a green space here, but the probability it comes up red or black is about 50%, right? And so what ends up happening here at this casino was that black, and it wasn't a rigged wheel. It ended up coming up black 26 times in a row, right? So think about what started happening with gambling habits if it fell victim to that gambler's fallacy. After it comes up black like 8 or 9 times, you're like, well, it's got to balance out, right? It has to come up red this next time. So people started putting money on red, like a lot of money on red. Well, it came up black 10 times in a row. Well, for sure it can't be 11. It's got to come up red this time. Didn't come up red. And so people kept, you know, betting highly on red, and it kept hitting black. And so people lost tons of money, which means that the casino made tons of money, right? And so anytime, if you know, maybe, I don't know, this could maybe help you out in your own gambling if you ever go to the casino or anything like that. You know, just because something happens, each single spin is completely independent from the previous spin, right? And so you shouldn't alter your behavior based on previous outcomes, okay? What else did I want to say here? I had something that I was going to bring up, but now I forget what it was. Oh, I know what it was. So another interesting thing is, if they're independent events, we said this has to hold. The intersection is just the probability of the events multiplied by each other. So if I think about coin flips or spinning this roulette table, the probability it comes up black on the first spin is what? About 0.5. The probability it comes up black on the second spin is 0.5. They're independent events. So if I want to know the probability it came up black on the first spin and the second spin and the third and the fourth all the way up to the 26th, all I would have to do is take the probability that it was black in the first spin, 0.5, times the probability it was black in the second spin, times 0.5, times the probability it was black in the third spin, times 0.5, all the way up 26 times. So I essentially have 0.5 multiplied by itself 26 times. which I'll just open this union data set up for now so we can do the math in Excel. So 0.5 to the 26th, 1.4, but notice in Excel, e to the negative 8 means move the decimal point 8 places to the left. So I move this decimal point 8 places to the left. I've got 0.000001. So I don't know, 0.00001% was how likely it was for it to come up black 26 times in a row. And you could do that with other things, right? What's the likelihood I flip a coin and it comes up heads 5 times in a row? 0.5 to the 5th, right? If they're independent events. I was actually talking with someone, since we have a little bit of time, I'll just mention it. You could actually, I mean, some of you might be completely unrelated or uninterested in sports, but you can apply this to any gambling. If you do look at sports betting lines, they do things like parlays. So every time they set a betting line, it's supposed to be a 50-50 bet, and you can bet 5 different games, so that reduces your odds of winning from 0.5 to 0.5 to the 5th power. And that's kind of how they work that out and give you better odds. You can do things like that, not just in sports betting, but other gambling as well. That's a little bit of an aside, but kind of interesting. You can kind of apply what we were just talking about to that. So I'm going to get rid of myself here for a second. And we'll do a little bit of work in Excel. I don't want you to get you guys too far ahead of the other section, but we'll start out and kind of build in this, and I'll mention some things. So we'll get rid of this because we don't need it. So I have in the in-class data folder a union data set. It's got 2 worksheets. The final one, which is hopefully what we'll be getting to by the end of the class, the very probably earlier than the end of class on Friday. But here's the blank one, which is the one that we'll start to build, right? So I've been giving you all the numbers for these contingency tables. You can build your own, right? And how do you build your own? Well, here I've got this data set where it has different industries. So like there's art and design, business and finance, computer mathematics. It's got a bunch of different year observations for each industry. And then it has what the union membership was in that industry in that year. So that's this one. It has what the union member weekly earnings are, and it has non-union member weekly earnings. And then I created this additional variable, which was just, well, what's the difference between union and non-union earnings? So I don't know what everyone's background is in here. If you had any econ classes, the general idea of unions is that we're suppliers of labor, like workers actually supply the labor, similar to like a monopoly supplies whatever the product is. But if I'm in a union and that's the only place you can go to hire electricians or whatever the job is, the unions essentially monopolized that market. And so they can now charge companies not higher prices, but higher wages, higher prices for their labor, right? And so if we look at these differentials, union workers almost in all of these, there's a couple times where it's not, almost are always making more money than non-union workers, right? So part of the reason why I use this data set is it's kind of interesting. Like if I didn't, like let's say there was a union, but they only made up 1% of the entire workforce, and I know that that union is going to demand higher wages, what would I do as a company? Well, if there's 99% of the other workers available that aren't in a union and they don't want as much money, I'm going to go hire them, right? And so the unions don't have as much power potentially to ask for as high of wages when they don't make up a large percent of the overall worker base. So we could do some things with this to try to figure out some maybe think we'll get to a result that's pretty interesting on Friday. But just as a starting point, I said, okay, what's the average union membership? So I took the average of this union membership percent variable, hit enter. So it's about 10%. What's the mean difference in union and non-union pay? Took the average of that variable. It's about $118. I could find the average for these two as well. So the average union earnings was what over in here. And then the average non-union earnings, excuse me, was right here. That's all stuff we've done before. And that just kind of gives me a starting point to kind of know what's going on with these variables. So you can kind of see there's a difference between union and non-union earnings here. And when I look at the average difference, right, I see that play out as well. The average membership is about 10.7%. So I'm going to do something. I'm going to create a contingency table. Okay. Now I'm going to use some cutoffs. So usually I'm just telling you events A and B complement, R1, C1, right? When we actually have an example and some data, those will have names and those will mean something. So if I think about what my event A is going to be, my event A is the differential in that industry between union and non-union workers more than or $100 or more, right? So if I say that that's my event A is the difference $100 or more, what would event A complement be? Well, it's everything that's not an A, so it would just be is that differential less than $100, right? Which is what I have here. So this is like A and A complement. All right, let me make sure there's nothing like that. My event B, I'm going to define as, is the union membership in that industry 10% or higher, greater than or equal to 10%, which would then make B complement, is the union membership less than 10%. All right? So I'll put my cutoffs up here, and we'll see why this is important as we kind of work through this example. I'm going to use 10% and $100 as my cutoffs. Now, in an assignment or something, this will be given to you. Here, I chose them because they're pretty close to the means, right? I know that they kind of split the data to a degree. You know, anything higher than 10% means that it's, you know, in the top half almost of industries in terms of union membership percent. And I know if they have a wage differential of more than $100, they're around the top half. So I can play around with these cutoffs later, and I'll show you that we actually can. But for now, we'll just use them to define our events A and B. So what we're going to do first is, when I was showing you those contingency tables or those joint probability tables, you had probabilities. You had 0.1, 0.4, right? But they started out coming from somewhere else. So the first thing we're going to do is we're actually going to build a frequency table. We're going to count the number of observations that are in each one of these categories. We'll still read the top 4 left cells as intersections. So here we want to count the number of industries that have a wage differential between union and non-union workers of $100 or more and have union membership that's 10% or higher. Right? So we only want to count the observations if those things are true. Well, we've used a formula that's pretty handy when we have criteria that we want to set and then count observations that fit that criteria, which is that count ifs formula. Right? So that count ifs formula, what I'll do is say, okay, the first thing I want to do is look through this difference in earnings variable. So I'm going to Control Shift or Command Shift on a Mac, hit the down arrow. I got to scroll all the way back up, which is kind of a pain. All right. I want to count it, so then I'll put a comma. I want to count it if this variable is greater than or equal to $100, right? If that differential is more than, greater than or equal to $100, $100 or more, sorry. So greater than or equal to, that goes in quotation marks, so just the same as when we were using the count ifs before. We'll then use an and sign, and instead of putting $100 in, I'm going to select my cutoff here, okay, that I put in another cell, right? I'll then put another comma. The second thing I wanted to check, and it's kind of, I don't know why it's putting this over the top of it, but remember, the second thing we want to know is the union membership 10% or higher? Right? So the second variable I want to look at is this union membership percent. Now, I could select this variable, then scroll back up. To me, an easier way to do it, since I know now it's in column C, I know that the data goes from cell 2 to 736, so I'm just going to type it in. C2, and then colon to C736. Just because I'm on a laptop and scrolling without, you know, a mouse or something, it's kind of a pain. That's another way you can do it. I have another, I guess, shortcut. I'll then put a comma. So I wanted to count it. I already counted it if the differential is $100 or more, but now I want to count it if this membership variable is greater than or equal to 10%, right? And if I look at the actual variable, it's already in percentage format. That's why I'm using 10 and not 0.1. Okay. Are there any questions on that before we keep moving? Okay with that? So it's similar to what we were doing before. It's just before when we were counting, we were looking at like the same variable. Now we're looking at every observation. We actually are checking to make sure that two different variables meet two different criteria. Does this first variable, is it greater than or equal to 100? And is this second variable greater than or equal to 10? Right? So we're using it slightly differently, but once we have that in there, it'll give us that frequency pretty easily. Okay? Now from there, I want to use the same process to count the number of industries that have $100 or more wage differential and also have below 10% union membership. So this is going to be, I'm going to have to type this exact same equation in, right? Except for now it's going to be greater than or equal to 100 and less than 10. So there's two ways I can do this. The first way is going to be, well, I'll show you one way and I'll show you the way I think is probably easier. If I select this, or I can select it up here even in this little toolbar, or this kind of, I don't know, it's part of the toolbar up here. I can copy this, right? I'm going to hit enter to get out of that cell. If I double click on this cell, or I go up to this bar and then paste, it won't update the cell references. So when I drag it over, that's when it updates cell references for me. If I literally like go up and use this bar and copy and then go to the cell I want it to be in, go to the bar and paste, it won't update any of my cell references. And that's kind of nice because I wanted the same thing. It's just now, let me make sure that you can see it. Now I still want to check to see is this difference variable greater than or equal to 100, but now I want to check to see if the union membership variable is not greater than or equal to, but less than, right? So all I want to do is change a sign, so copy, paste, change the sign. Cool, now I got that. Now the other way I would do it, because that we're gonna have to copy and paste here, change the signs, copy and paste here. An easier way is probably, I don't know if it's easier, that's the way I would do it. We'll freeze everything, right? Because I want to keep looking at the same data and using the same cutoff. So I'll select the cell references, F4 or FNF4 on some laptops, and then on Apple Alt-T, no, not Alt. Why did I say that? Command-T. We'll put those dollar signs in there for you. So I'm going to select these cell references, put dollar signs in, right? Once I have all my dollar signs in there, now I can just copy across, copy down, and now I'll just go in and change my equality signs, right? All right, so this one would be like less than. This next category, it's going to be less than $100, but still greater than or equal to 10%. And then for this one, it's going to be, is it less than $100? And also, is it, delete this, less than 10%, right? So once I copied it over, I'm really just going in and making sure that those inequality signs match up with whatever the row and the column headings are, okay? Anybody want to see any of that again? Okay. All right. There's no questions on that. We got a little bit further than kind of the other class, so I'm gonna stop here so I can start you guys both off at the same place. So I probably will put that poll out just to make sure that if you do want to show up in class, I'm getting you here as often as I can, because kind of getting low numbers, and like I said, I haven't been getting as many emails about people needing to quarantine. We'll be back in class on Friday as well. Everything's kind of back to normal now. I'm 100% and excited to be back and see a few of you. We're going to work through the rest of this Excel assignment on Friday. I will likely then post an Excel assignment once we've completed working on this one. So I'll likely be posting it Friday. It depends if we don't, for some unforeseeable reason, I don't get through it all on Friday. We might hold off until Monday. Obviously, we were supposed to have an exam next week on Friday. We'll see. I think I'm going to postpone that probably. At the very least, push it to that following Monday and do like an in-class review session on Monday. And then you have the rest of the day or all of the day to take that exam on Monday. Or maybe I'll do like a 24 hours. After the exam review is over, you have the next 24 hours to kind of get on and get that exam done. And we'll talk a little bit more about that next week. And on Friday for sure, I'll kind of thought about whether or not I want to push it to Monday or even maybe a little bit further out. Okay? Any questions for me before we get out of here?
I had questions on the Connect.
Okay.
Can I share my screen with
I don't know why you're so quiet. Hold on. Can you ask your question again?
Can I share my screen with you?
I can. Here, I'm gonna end class here, and then I'll get your question answered. Okay. All right, let's go. So I'm gonna end class there. I'll keep Zoom open to kind of help with some last minute other questions, or if you have questions in person, you want to stop by, I can help you with them up here as well. But we'll stop the recording there, and I'll see you guys on Friday, or some of you on Monday.